Okay, let me improve a little bit this. I think you can see now the presentation better. Basic principles of the observers and Kalman filters. Observer or observers about the Kalman filter, of course, we need many lectures to understand what he is. But he's an observer, or better to say, one of the possible applications is exactly to use this algorithm as an observer. What is an observer? I try to clarify now, but before starting with this important concept, observer is monitoring. Observer is estimation. I try to use some different word in order to give you a feeling, because an observer is characterized by mathematical definitions. This means it's characterized by the equations. I will use about a little bit later. Just some some elements for the first part of the sessions. We have some sessions. We consist of lectures, but independent of this formalism, we can see here 3 points. Today and next week, we will see some elements of the observability, and we try to understand what an observer is, but not only how we can build an observer. Already, I would like to say next week, I will show you the software of an observer, not Kalman filter yet, but an observer. In fact, also the director say, but if you don't do just the observer, the idea was to change a little bit the name, but basically is Kalman filter, the course, which is an observer. And then the central part of this session of the course is we will introduce the discrete Kalman filter. We can see here some interesting words as a dynamic state observer. Dynamic state observer. I will come back on the word dynamic state. Modeling of industrial control system. Industrial, you can forget now, because we will see that we can use the Kalman filter everywhere. Very important that we need a dynamical systems, not necessarily industrial, not necessarily control. Of course, very often is used in control. As I told you, I'm here professor for control systems, but not necessarily can be used for monitoring. Monitoring means, yeah, means to observe, means to try to describe what happened, what happens in the system. I will come back on these words. And then, of course, in the first session of the course, also MATLAB Simulink. I don't know if you know MATLAB Simulink. Of course, I don't have much time to speak about MATLAB Simulink, but using the software which I already prepared, using the software which I already prepared in the term of some applications, general applications. Sometimes general means abstract applications. As I told you, don't care about industrial control systems. Originally, the course was conceived in another context. Of course, I can change the words, but believe we can apply in every kind of dynamical systems. We will see what a dynamical system is. And the application means, at least in our course, but also in the project, to use MATLAB Simulink. First of all, it's the more powerful software which we have in terms of simulation, modeling, identification. And secondly, you have to know that in Loifana, we pay per year $30,000 per the research for the license. We have the license for the students. You can connect your remote and you can use all tools of MATLAB because you are a student in Loifanna. This means you have to use MATLAB in any case, because the risk that we lose this privilege to have at disposition the tools of MATLAB. Okay, at the end of this slide, we can see the picture of Professor Kalman. The name Kalman filter, or the denomination, better to say the denomination Kalman filter, came from Professor Kalman. I met the Professor Kalman once in my life, just to understand just where the name come from. It's the name of a professor. It was professor. He was professor in America, I think in Illinois. I don't remember exactly. I think it's Illinois. But at the end of his career, at the end of his life, as an emeritus professor, was a professor in ETH Zurich in Switzerland. I met once in Como, in a conference, and not personally in a conference. I heard in a talk. Um, it was very nice an answer. A professor asked him, "Excuse me, Professor Kalman, I would like to understand when Kalman filter doesn't work." The sense of this question was this. You have to know the Kalman filter is really applied everywhere in the sense when we need to identify parameters, states, sometimes also to predict. Anyway, in modeling, simulation is extreme, very often used. And it seems that is working very well. For instance, in cruise control, I work in cruise control in Volkswagen. We apply the Kalman filter. In auto parking in Volkswagen, we apply the Kalman filter. For COVID control means to be able to estimate how many people have to vaccinate per day. We use the Kalman filter. In insulin control, in diabetic system, we use the Kalman. Anyway, it's really used in psychology. We use the Kalman filters. Not only the Kalman filter, but also Kalman filter. We are working in a couple of projects in medical systems using Kalman filters. Also in prediction of feeling. We have a student. I hope to organize a seminar with him. We have a student with which we try, is a master thesis, data science student. We try to predict the feeling of the bipolar defect or the illness. I don't know if you know that. When you are down and then up with a very high frequency, and this peak between feeling high or the mood high and mood low, this two peaks is very large. In the morning, let me say, very down. In the afternoon or in the evening, very up. It's a psychological or yeah, let me say, disturbance. Anyway, it's really applied in many possible and different applications. Therefore, we will see in this course, after some technical examples, I will try to show you, let me say, I will change a little bit the approach, and we will see very abstract systems, mathematical systems, which can represent bank systems, which can represent biological systems. We will see also in possible population dynamics. Anyway, quite general applications. Let me go ahead. Here we have possible literature. Don't buy the books. Probably you can find also these two books, books number 2 and books number 3 in internet. The reference for is not a book, it's the original work. The original works of Kalman. You can find this also in internet. Please don't read, because you can read, of course. It's extremely difficult to, I would like to say, to understand. I mean, I am reading this book, excuse me, this chapter also now. Even though I am working with Kalman, I started working with Kalman filter I don't remember. I was relatively young. I don't want to say one, but each time which I work with Kalman Filter, each time which I read, for instance, this paper, but not only this paper, I discovered always, every time, something new. It's a really difficult paper to be read. But in any case, I put it here just, you can download, you can find, just to show you that we started, or the better to say, Professor Kalman started with this investigation a couple of years before the publications. This means you can realize how many years we, let me say the humanity of, let me say humanity is a little bit too, this is particular expression, uh, the scientific community is working on this algorithm with different, you understand now why different variations, application in all fields. Very important is the reference number one. Reference two and three are two books. I don't have here, but I have in Lüneburg. I will show you the books because sometimes I need to show you how complex or boring in the meantime are the demonstration. But you don't need to buy the book. Some of them, I think, the second one you can find also. I don't remember. Yeah, I have in hard copy, but you can find also in PDF for free. Very important is reference number one. But at the beginning, don't download. It is free. You can download, of course, but it is difficult also this to understand because it's so good, but in the meantime, it's extremely compact. This means it's useful after some lectures. When we, let me say, when we will conclude with the basic knowledge of Kalman filter, I hope you can download it, you can understand this. Is a very compact introduction. In fact, it's written introduction to the Kalman filter. In this sense, singular. Why singular? Again, because in this paper is considered the basic form of Kalman filter. This means no variations. Yeah, probably one variation, but the variation is considered as a basic form, the extended Kalman filter. But about the nomenclature and so on, we will do. I will be more clear during the semester because you can understand how many years the community work on this. It's more than 60 years. No? It's clear that nomenclature variations. We have many things. Okay, now starting. Observer, observability, systems, modeling. I try to clarify the glossary. Some elements on the observability and on the observer. Yeah. To speak about the observability, better to say, to realize an observer, for a system, we have to verify that the system is observable. Before starting this could be better to say two words about the system. What is the system? Yeah, the system is a quite difficult concept to be explained with words. But I want to avoid the mathematical definitions because we have more than one, because these are more complex. For instance, we say the scholar system, the brake system in the car. Everything is system in the sense. It's an structure. What is the difference between model and system? Now probably we can understand better. The model is the description of a system. Not necessarily a mathematical model, but in our case, it's a shame, yes. We are speaking not necessarily, but it's the goal at the end. A model of a system, the bank system. Now, this could be probably understandable. A bank system. interest, rules inside our investment, everything which we know already. Is in a system, is in a structure of rules. Now, in the sense of structure of rules, of course, we can consider this mathematical model because also mathematics are, is based on rules. Now we can have a feeling about what is in a system, what is its representation, in particular, and a representation based on mathematics. Now, observability and observer. I have a system, I have a real system, I have a bank system. Um, the bank system can be characterized by two elements which we call states, liability and assets. This is an impossible representation, impossible, but not the unique one. Liability is the money which belong to me, but is in the bank. It's a little bit different between capital and liability because the liability again is the money that belongs to me, is my money, but it's not by me in the bank. This is a big difference because isn't a difference at least I would like to say because without this concept which is not by me, we don't have the dynamical system. I mean, the bank is the dynamical system, again, another concept, dynamical, because my money, which is mine, of course, but it's not by me, increase also without, but let me say increase, without, it's true, no, it's valid, this is what I say, without that I invest or I put money in the bank. Because the system, let me say, because of the presence of interest, increase the money. This means uh, that somehow the money autonomously increase. This means dynamics. I mean, if the interest is zero, I don't receive interest. Uh, the system is static, it's not dynamic because the money changes just if I put money in the bank or and if I withdraw money from the bank. Roughly speaking, in my wallet or at home, if I have money at home, of course, the money that remain the same as long as I don't put the money somewhere or I don't take away the money. This means the concept of the dynamics is extremely important to characterize or these changes, if you like, the dynamical systems. Liability, this money, represent the energy of the system, represent the state of the system. The reason is that I can accumulate, it's a good example, money, or I can waste money in the sense. Waste is not exactly the good word. I can spend money because I cannot destroy this energy. Very important concept. If I have money, I cannot destroy the energy. I can transform the money into, I can buy the car, but I cannot waste. About that, probably if you are expert in economy, we can understand better. I'm not expert. I can explain better if I consider technical examples. I mean, do you remember in high school, just shortly because I want to go ahead, uh, we say it's not correct to say that we waste energy, but we transform energy from electrical energy in movement. The variables which characterizes this energy, the name is state. Liability is in a state. Assets, I don't know if you know economics, but the investments, everything which is related to the property and the assets, the other state, the other energy in the bank. In system, technical system, we have, for instance, we will see in a few minutes, energy like, correctly, I have to say that money, in the sense liability to be precise, it's not exactly energy, it's a pseudo energy. Because typically with energy we intend or we consider the classical physics energy like electromagnetic energy, electrostatic energy, kinetic energy, potential energy work. Anyway, nevertheless, we can say energy because we can store and also we can transform. Okay, again, observer is a structure, is an algorithm which allow to monitor the liability, the assets, the energy, it doesn't matter which kind of energy, through a state. State is a variable, and we will see that in the mathematical meaning variable is a word which we use also in math 1, math 2, and so on. Of course, to build an observer, which is an algorithm, we have to verify that the system is observable. It's observable. This means we have to verify its observability. Now, about this linguistic aspects, I think I gave you a lot of some feeling. I would like to go ahead now. Look more concretely. You can see here in a possible graphical model. Please pay attention what the word about my explanation. We have a system, this sigma here. We have another structure. At this moment, it's quite abstract, but we will see next week that I will build mathematically an observer. An observer is in a mathematical description, not only, but could be so considered. It is. Basically, to be precise, is an algorithm. Kalman filter is an algorithm which allow to estimate parameters and state of a system sigma, even though I don't measure all elements which I can measure. We can see here, let me say, the sketch. I measure just one output. About the output, what is an output is intuitive. I don't want to go really in depth on this because also input and output in the system, in system theory, we can use a mathematical definition. But anyway, it's intuitive. An input is what I put as a, let me say, element to move something. I invest money. I invest money. I put more. I put money in the bank. Money. If I put money in the bank, this is an input. Intuitively. When I withdraw money, of course, this is an output. It's intuitive to understand. We will see now in technical systems, probably a little bit more complex, but I try to explain better. I measure liability. It is easy to measure the liability because it's the money which I know, which I have in the bank. And then I have to estimate some different elements connected with the liability, assets, for instance, even though I don't measure assets. This means the algorithm is something useful for us because sometimes some concepts is really abstract. Some concept, some element is not possible to be measured or it is too expensive to be measured. But an observer allows to give us information about, let me say, elements which I don't want or I cannot measure. Or really is a concept with it is not measurable because it's abstract. And then I can use this element x hat, which is the observed state, liability, and assets for instance to control. But forget at this moment the control aspects because we are not here to learn control. About separation principle at this moment, forget. I will come back later, probably if I have time. Yeah. Let me now go more concretely on the problem, so we can start with some equations. It's a shame I have a technical example, but I will consider also different examples later, but very important abstract examples, because you will realize that we can consider any kind of systems. biological. Biological means population dynamics very often, but not only. Sometimes we are able also to estimate, let me say, concentration of chemical reactions. I'm not expert on this. No? But let me consider a DC drive. For the engineers, it's easy to understand. For not engineers, a little bit boring. But the goal is not to clarify the DC drive, is to introduce the system, the concept of the system, to introduce what is an input, what is an output, what is the model, in particular dynamical models. Look at this example of a problem formulation. If I give you a DC drive is in, I don't know if I have it here. Yeah, here. Now, with this model, with this graphical model, please pay attention. The word model is used in order to indicate a representation. This graphical representation, we have I sketched in DC drive. Let me come back and then we will see again this. But in order to understand again the word model, this is the model, but in a graphical model. Is this enough to apply the Kalman filter? No. This is just a pre-step in order to build a dynamical system for observation, for monitor, and so on. But of course, in a model. Sometimes in the literature, model equals system. You have to be clear what we intend. To be more precise, we say real system. This is not a real system. The real system I don't have here, I have in the lab, real in a physical model. But this is in a system, of course, in a graphical representation of the system, to be precise with the words. But let me come back here and then we will go ahead. If I give you a DC drive, in a real DC drive, the idea is, a possible problem formulation, estimate the velocity. Velocity in the sense could be rounds per second, probably the engineer understand directly what I intend. Of this motor, of the motor, using the measurements of current and input voltage. This means I don't measure the velocity, and I try to estimate. Please pay attention. Estimate, to observer is the same. Very often we are used as with the same meaning, even though we have a difference. An estimation is an observation, excuse me. The observation is not an estimation in the sense estimation is an observation as an optimal observation. I will come back on this when we speak about the Kalman filter. Kalman filter relies on estimation. We will see at the end of next week the Lundberger observer, which is an observer, is not an estimator, because in the basic form, the Lundberger observer, Lundberg is the name of the professor, we will see today also, a little bit, does not realize in its basic form, does not realize an optimal observation. It's an observation, but not the best one, which we can find. When we speak about the best one, we have to be careful, because best one means that I have to consider an optimal procedure. I have to consider criteria in order to say is the best. We will see. Kalman filter is an optimal observer. But go ahead. Of course, I can estimate also the current, even though I measure. Good. But the question is, if I measure, why have I to estimate? There is a theorem that under some conditions, the estimated current or the estimated variable is better. When I say better, again, we have to define an optimization frame. We have to define criteria, but estimated is better than the measurements in accordance with some criteria. This is the Kalman filter. Therefore, we used the estimated variable and not the measurement. But it's easy to understand also practically. If you think about the word filter, Kalman filter or filter. We filter the signal. This means if I have a noise, if I have something wrong in the measurements, because the measurements introduce also errors. If we are able to define some criteria, some methods, now the word filters with plural, of course we can eliminate or we can try to eliminate a part of this error, faults. Okay, now more technically, I think I don't need to comment this picture because you know from high school, not only the engineer, no, we have magnetic fields, in this case generated by a permanent magnet, it seems to be, but not necessarily, could be also uh, electromagnetic magnet. In this case, I indicated permanent magnet. North-south is the model. North-south is a magnetic model. Do you remember probably the engineers know that we have also different model of the magnetic phenomena. Huh? I don't know if you know the words waves. The magnetic phenomena can be modeled also in the presence of permanent magnet with waves. Of course, it's a little bit more difficult, but anyway, I am not expert about the physics in the sense. But it's the model. What I'm showing you is the graphical model. In any case, I can say so. Which we have the magnetic field. We have in the middle of the magnetic field the electrical part, which consists of a coil in the rotor. And this basically also in high school, in course of engineering, we say that we have two systems, two physical systems, an electrical system, which consists of coil in the rotor, or of the rotor, if the motor consists of a rotor, because we have also motor which is linear in its design, in its geometry, and then we have a mover which is not a rotational mover. But anyway, the second element, the second system is the mechanical system, a real system, which consists basically of the moving part, in this case, consists of a rotor. Yeah, we can see here in this slide, if you remember, I repeat for you the question, which is basically our problem formulation. No? Basically, it is possible to estimate the velocity of a motor if I measure current and voltage, or if you think about the bank, it is possible to estimate assets of the bank measuring my input money and the liability, or yeah, at this moment I told you about just of these two possible systems. The question is, it is possible if I can be an observer. But of course, as I told you at the beginning, to be an observer, we have to verify, or at least we intuitively we can understand that we have to verify if the system is observable. This means we have to check its observability. Now I will go a little bit more in depth on this concept here. Very quickly about the model, because the course is not only for engineers. I will build the model, the mathematical model of the system. The engineer is clear what I intend with this slide. We have an electrical circuit which characterizes the electrical, yeah, to be precise, remember I told you that I have a two system, electrical system and mechanical system. I forgot to emphasize this first sentence, two coupled systems. They are not separated. This means basically we have a system which consists of two subsystems which communicate together, coupled. To answer the question, nevertheless, it's a shame we need to build a mathematical model. Moreover, we need to build a dynamical mathematical model. Dynamical means practically or mathematically means using differential equations. Probably you learned in high school. In high school, I'm not sure, but in Math 1, Math 2, differential equations. Yeah, this equation here is the induced voltage. We can be see localized here. Believe me, it's not the topic now to understand this actuator, but we can see that this induced voltage is in a reaction, with respect to the movement. I mean, moving the rotor inside the electrical field, we generate a voltage which works against the current which is generated by the voltage input. In physics, very often these kinds of phenomena. In this case, in the electromagnetic field, we say Lenz law, Lenz phenomenon, and so on. Let me go ahead quickly. But we can see in a connection between the mechanical aspect, omega is the velocity. I forget here to write, but I'm telling you now. And U input mean value is the reaction voltage of the movement. Now, building here the Kirchhoff law, which I am showing you here in the middle of the slide. Kirchhoff law for the engineer is clear. No, it's the balance of the voltage of the elements which we have in the electrical model. What we are saying now in the graphical form is an electrical model. Why not? In graphical form, of course. And in the middle, we have the mathematical expression of this, let me say, model, which is a representation. Basically, I am using different languages, different model, different representation to converge in a mathematical representation which I can use to build the Kalman filter. Again, starting from a graphical language. Language is also a model because the language is also structured with rules. Very important concept. The system, the language system, we can say, I'm not linguistic, but if you digit in Google language systems, you can find Arabic, you can find Latin. I'm not expert, but believe me, the language is in the system because we have rules. But I'm not expert about that. But system is very important word. Again, here's the Kirchhoff balance. I don't want to clarify this because it's not the goal at this moment, but the engineer is clear what I intend. The voltage, you input minus the voltage, which I lose, I would like to say, in the resistance in accordance with the Ohm law, and then L multiply the derivative of the current is the voltage which I can localize in the coil, and then the voltage which I try to clarify in the lens effect equals zero. No? The balance. No? If you remember, at least the engineers, this equation represent the conservation of energy. No? Very important, as important for everybody, that we have a derivative. Do you remember about the concept of the dynamics? I told you dynamics is what I'm looking for. Dynamics means changes. Here we have the derivative of the current. The current represents somehow the electromagnetic energy, or represent is not a good word, reflects the electromagnetic energy. Because if you remember in some courses in electrotechnic, the electromagnetic energy in a coil, which is characterized by L inductance, is 1 divided to L multiply current square. The current reflects directly the electromagnetic energy, which we can see here in this balance, plays an extremely important role. It changes. In fact, look at the middle. I express now my balance in a particular form. Look, the change derivative, you remember in high school, derivative means changes. Do you remember this? But changes means dynamics. I am playing with the words. I'm playing with the words. This means the change of the current will reflect energy. This means the change of energies is equal as in a complex expression. It depends on the input. If you think about the bank system, of course, the liability, which could be represented by the current, in our case, which is the state. We say state, everything which reflects the energy. It doesn't matter if current or liability. Depends on what I put in the bank or what I withdraw. Your input could be positive, could be negative. In the bank is clear what I understand, what we can understand, excuse me. It's clear what I intend. If your input is positive in the bank, means I put money in the bank. If the input is negative, I withdraw money in the bank. Of course, change the liability, but in order to change the liability, change the derivative, no? Because the derivative is zero in a variable. I don't know if you remember in high school, means no changes. Of course, here we can see that the current change also not only because of the input, but change because of the current itself. A change because we have an interaction with the velocity of the motor. In the bank is quite similar. The liability L, which in our case is the current that is reflected by the current, change also from depending on the liability itself. Because if I have more money in the bank, I have more interest. This means the derivation, the derivative, the changes of the liability, the derivative of the liability change also is the function of the liability itself. I will show you the model. It's quite similar to this one. What is omega in the bank? Is the assets, the property, the capitals. By the way, I'm not expert in economy, but I have the model. Okay, independent of this R inductance, let me go ahead to conclude. We need also to characterize the other part of the model, which is the mechanical model. We can see here in this disk that we have three torques or moments, the motoric moment, and against the motoric moment, we have the inertia moment and the friction moment. Probably you remember a little bit from gymnasium, different equations or balance. Do you remember? M mass multiply acceleration equals the sum of the forces which act on the system. Here, we don't have forcing, we have a torque, a little bit more complex. We have a moment because we have a rotational movement. But anyway, in the same way, we have something which moves the rotor, which is characterized by a constant multiply the current because everything came from the current. I mean, again, we don't waste energy, we transform energy. We have electrical energy, which is going to the system using using the input or the voltage. We store energy in electrical energy in the coil, and then we transform a movement. Anyway, at the end of everything, we have this balance here, which is quite similar to the balance before. We have just to remember that the derivative of the velocity is the acceleration. Do you remember in high school, mass multiply the acceleration equals the force acting on the system. Here, J reflects the mass, is the inertia. The mass is an inertia. We can see that J here, don't learn this, just to have a feeling. Depends also on the mass, on the dimension, geometrical dimension of the rotor. It's a complex because it's in a drive, it's in a motor. But anyway, the equation here in the middle, reflect exactly what we learned in high school. Mass multiply acceleration, but the acceleration is the derivative of the velocity, the change of velocity. No? Please pay attention. I am looking for dynamical system. Should change, should have a model which reflect the changes of the energy. Which kind of energy we have here? Kinetic energy. Kinetic energy, which is characterized by the omega in this case, by the velocity. No? Do you remember in high school, 1 divided 2 mass multiply velocity squared? No? This is the energy, kinetic energy. Then we have on the right part the motoric force, which is characterized by the current. We transform the energy. No? And then minus because we have the friction. I don't want to go in depth on the model. No? But at the end, very important, we have a similar expression as before, in which we have the derivative of the velocity. This means changes of the velocity. This means change of the energy equals something, let me say, complex, but depends on state. This equation here, then, these three equations, the equation number 2 I didn't clarify, but it's extremely easy to be clarified. That say the derivative of the position equals the velocity. Is also important sometimes because also this equation is an energetical equation, because we don't have just position and velocity at state. State means variables which characterize the energy. We don't have just current and velocity. We have also the position, the work. I mean, traveling from Lüneburg to Hanover is not the same energy, even though I have the same velocity, if I travel from Lüneburg to München. The reason is the distance, the work. I need more work, even though I have the same velocity. I have to work more to reach Munich. Okay, equation 1, 2, and 3 are the equations which characterize the dynamical systems because are expressed in terms of derivative of the state variables. State variable reflects the energy. We can see on the right part input and states. You input in the first equation, just in the first equation, because the input is going through the electrical system, which is totally described by, well, totally I don't want to say, but is mainly described by the first equation. Of course, we can see the current also present in the equation number 3, because as I told you, the system is coupled. Omega is also present in the equation number 1 and equation number 2. The system is coupled. Must be coupled. If it's not coupled, we will see we cannot build an observer. We cannot build an observer because we don't have connections in between. This means we don't have the observability. We can speak about the level of observability, of course. Look, if KE is very small, if KE is 0, for instance, we don't have this element here. This means we don't have the connection between electrical and mechanical, better to say between mechanical and electrical. In the sense it's better to say so. This means measuring the current. I cannot have information about omega or the velocity. I will come back in 1 minute. 50 minutes, and not the language, not the model, not the form of the model. I don't know if you remember the theory of the representation of the system using matrices and vector. This representation here is equivalent to this one, but more suitable to build an observer because with matrices and vectors, we can easily implement an algorithm in the computer. This means we clarify for the students who don't know the language of the matrix and vector a little bit this language here, or the better to say this model. But just to sum up, starting from the physical system, which I don't have here, I have a lab. I try to represent, to model the system using a graphical representation. And then using physical insight, mathematical and physical insight, I will, before physical insight, I use the technical scheme. I mean, this model here, this graphical model, exactly is not the same like this. This is a little bit more, how possible to say, it's just a practical graph. No many physical insights here, a little bit. This technical scheme, I will speak about scheme in this sense, electrotechnical scheme, yeah, we can see more physical insight. But both are model, both are two ways to describe the system. And then go in depth really in the physical aspects, I can build these 3 equations, which we need to build an observer. But if I want to build an observer, and a quantitative observer using the computer, typically we used matrix and vector Of course, if you want to realize this or use this model here for an observer, it is possible. It is possible, but we need a particular calculator, does not exist anymore. I don't know if you know the calculator which use the operational amplifier. Operational amplifier. You can use also this one, but it's not so suitable, I would like to say. Today, with the use of a microcontroller, typically everything is represented by matrices and vectors. This means this information here, I can translate in this form here, in which we have the same system, because if you remember the rules from the product between matrix and vector, we can see that rho, the derivative of the current equals, like here, the first line. First row multiply this column. If you remember the rules, minus R divided L multiply the current, which is here. Minus R divided L multiply the current, plus 0 multiply phi. Why 0 multiply phi? Because in the first row, we don't have phi. Then minus Km apostrophe divided L multiply omega is also there. Please pay attention, Ke apostrophe equal Km apostrophe. I didn't insist on this technical aspect. It's not the goal of the course of this lecture to clarify the model of the actuator. We have a model. And if I do a plus 1 divided L U input, we have basically the first equation. I don't want to insist on this rule because many, I think you know a little bit. But anyway, very important, I transform this system here into this one because it's more suitable. Each transformation should help us. We will see using MATLAB simile also next week that to represent in the actual in the microcontroller which we have at disposition is extremely easy to use matrices. MATLAB Simulink is just a tool. We can use also different tools, different software, not necessary to communicate with the microcontroller. This equation here represents the output equation. What we are measuring? We measure the current. It's a trivial equation, but for the computer, it's not trivial. We need to do that. I will come back on this. Look at this, very important now. I try to reduce the model. Why that? I try to reduce the model. We can understand better in a few minutes. But I would try to introduce now the concept of this observability in a practical way, in a practical form. I cancel from here, let me say, the information in the middle. The derivative, I eliminate the derivative of the phi with respect to the time, the central row, this eliminate the phi state, eliminate this element here. Why that? We can see also from here that we have a row, a column, excuse me, with all 0. In this matrix, the matrix in a table, this matrix in a table, in this table, in this matrix, this means that I don't have connections between phi and the other equation, or better to say, between phi and the other dynamics. This means if I measure phi, of course, I need this in the model. But if I don't measure, because you remember the original problem was it is possible to estimate the velocity measuring input voltage and current. I didn't mention the phi. No? This means if I don't measure phi, I don't need phi. The reason is that I cannot, please pay attention, observe phi. I clarify now this equation reduced in this form here, if I don't consider phi. I clarify this using the scheme here, which is another model, which is another structure to interpret or to describe the system. This is the language of the block diagram. I will come back during the semester on this. At this moment, let me go ahead because I would like to conclude in 10 minutes. I would like to be able to introduce the concept of the observability, but also using this kind of scheme, which can be better understood with a little bit more easy example. But assuming that we are able to build this, we will see in a few minutes here. We will see in a few minutes for different, a little bit more easy system. Assuming that we are able to build, look, the message which I want to give you. Do you remember the proper formulation? I measure your input. I measure current. Basically, I have an instrument here. You see my hand. Let me say my hand. I have an instrument here. It is possible to, question was, is it possible to have information about omega? The answer is yes, because of the presence of this feedback in the system, structurally in the system, physically in the system. Do you remember Lenz's law, Lenz's effect? Km or the Ke, Km equal Ke, apostrophe is just in the literature, if you read some books, sometimes, not always, apostrophe means everything is round no, apostrophe is radians instead of round. It's just a formal thing. Km equal Ke in our motor. This is a structural condition. This means at the beginning I told you about Ke, but I put Ke equal Km. But in any case, because of this back effect is the name, a little bit more complex the name, but this is a back effect. I will have here also information about omega. This is intuitive. We will see mathematically what is the meaning. But I don't have here, it is important this scheme here, information about phi. It's clear because we don't have feedback, physical feedback, structural feedback, or the structural connection. This means in an observer, if I don't measure phi, I don't need phi. Very important to reduce the dimension of the matrix, because reducing the dimension of the matrix will reduce the calculation load. We will see extremely important in the realization, the practical realization of the observer, that the observer must be, how possible to say, the dimension of the matrices. Let me say the number of the equation, the dimension of the matrix reflect the number of the equation should be the smallest possible, because we pay the price in terms of calculation load, in principle. And calculation load costs. I will come back on this word cost. Cost in all meaning. Cost in terms of time, but cost in terms of money, because we need more memory, we need more faster microcontroller. But I will come back on this, because at the end, the goal of the course is to realize the Kalman filter. This means we have to receive also feedback or the feeling about how cost. In order to understand, I'm concluding in 5 minutes. I come from industry. I told you once what happens to me. I come from industry. I work a lot of years in industry, in a research center of industry, but in industry, before becoming a professor in different countries. But I remember here in Germany, in HBB Heidelberg, I worked 3 years, more than 3 years. I received the task to build a system based on Kalman filter to recognize errors. I don't remember what system was. It doesn't matter. I present my work in a meeting with the chef. The results, the software, everything, validated by the data which I receive from ABB's Asian Brown Bovary, and we have also in Hamburg. And the chef told me, how much cost this microcontroller, which we need to implement this algorithm? I told it cost €1 more than the actual what we wanted to implement. He thought a little bit, answered me, For us, it's better to leave the error in the system. I don't want to implement the algorithm. In order to understand how is important to realize at the end something which is feasible also economically, no? Because believe me, €1 more, if you have to produce, I don't know, I don't remember in ABB, but let me think about also Volkswagen. We produce, I don't know how many car per day. Of course, in this case, €1 it depends how many microcontroller you need, but in any case, could be also not feasible in terms of economic. A few minutes to conclude because it's important now. Let me see this concept here. A few minutes. We come back next week on this general representation, which we can see x dot on the left, which is a vector. X dot, this nomenclature which I didn't comment. X dot is a vector, the vector of the state. Equal what? F is a function of x and u. It is, yeah. We can see a little bit better here. It's a function on x and u, state and u. And then we have also a possible output, what I am measuring. More than this, which is in general, until today, we have seen this linear case, or the second part of the slide. You remember the matrix A, the matrix B, the matrix C, the matrix D. I didn't insist on this representation because I will come back on this. This form here is in a particular case of the general form, which I haven't seen until now, in which A is the system matrix here, reduced, in which B is the input matrix, sometime input matrix. C is the output matrix. The output matrix in the observer is extremely important because characterize what I am measuring. D is in a particular matrix. I will come back on D also later, even though we used proper system. Proper systems have system with matrix D equals 0. 1 second. If you remember here, no? 0 multiply U input. D is the input-output matrix, the connection between input and the measured. In this course, we will consider system with matrix D0. We say proper system, which we don't have connection between input and measured state. Current is the measured state. Imp is the measured input. The measured input is not a state in our representation. Okay, I will introduce in 1 minute the lecture of next week. Next week, I hope to be able to show you also the software for an observer which is not a Kalman. Look at this. In order to clarify a little bit, but we come back next week. No? But you have the lecture, you can download, you can eventually read a little bit. I have these two equations, which if you see all together is in a system, because we can see that we have connections. Now, let me start with this, excuse me, with the non-observable. We have a system consists of two equations. Look, we can see that x1 appear in the right part, just in the first equation, but not in the second one. Interesting. Let me shortly justify the scheme, and then I will conclude. 1 minute. This scheme, or this language here, or to speak or to communicate with you with this scheme is the same, please pay attention, is the same if I communicate with the equation. Here we have an error. I'm not sure if I'm able to correct. U input here is the same U input here. I forgot INP. I try to correct, but I think this is a photograph. In the future, I would like to correct. But believe me, I inform. Your input here is the same here. How I can build this, this scheme? It's easy. Because look, if you consider x1 in this position here, between x1 and x1 derivative, which is here, the first equation, we have an integral, no? Because we know that the integral of x1, if I know the initial value of x1, is x1. This means no problem to understand that between x1 derivative and x1, we have an integral. Because if I have the initial condition of the integral, x1 derivative integral of x1 derivative with the initial condition of x1 equal x1. Now, x1 derivative, in accordance with this mathematical expression, equals x2, we will come somewhere, minus x1 itself. Look at this loop. Look at this loop. The dynamics is summarized in this loop with the integral, If I do the same consideration from the second equation, I will build this one. I will go in depth next week, no? But just to understand, now, the last sentence, if I measure the second variable, this means if the matrix C is characterized by 0, 1, this means I measure x2. I measure the second variable. x2 equals c multiply x. X is the vector, is not written here for sake of brevity, is the vector which consists of x1 and x2. X is the vector which consists of x1 and x2. Measuring x2, the system is not observable. The reason is, in the second equation, x1 is not represented. We can see here. Graphically means I don't have connections. Connection is this line. No? I don't have connection between, let me say, x1 and x2. But we will see next week more in detail everything. If I measure x1, this is a slide. This means if C is 1, 0, I can observe what happens in x2, thanks to this connection. Why that? Because in the equation 1, x2 is represented. Okay, next week we have more time because I don't need to introduce the course. I don't need to introduce myself. I hope we will conclude this part dedicated to the observer. It's not a Kalman filter, not yet. And I hope to show you, in any case, I will show you, or next week or after next week, the software, a little bit introducing MATLAB for students who don't know MATLAB. Of course, I don't have much time to clarify MATLAB, but we work almost every day with MATLAB. Questions? Yeah, I see a student with a question.
Professor Mercorelli, do
Yeah.
we need to install MATLAB on our computers?
No, you don't need a computer to attend the classes. You need a computer just for the examination. I mean, to realize the software for the examination. But you can use, for instance, the computer in my lab. When I will be you don't have a computer at home?
Hello?
You don't, do you have a computer at home?
Yeah, yeah, sure.
Yeah. This means the computer is useful to realize the project. For the lecture, you don't need.
Okay.
But we can use, because when I will be in Lüneburg, we will meet in Koratsuze room. You know Koratsuze room? The computer lab.
Okay.
I will indicate when I will be there where the computer lab is. Not only, you can use also my lab. You can meet in my personal, in the lab of control. I will show you. At this moment, you don't need anything. Of course,
Okay.
when we start to realize the project, somehow we need a computer. When I will be in Lüneburg, I hold the lecture in a computer room. This means you can use the computer. It's not so in really, but you can use, because I will upload the software and you are in the room with me and you can download it. You can do also from home next time, of course, because next time I will start with the software. But believe me, it's not so. necessary to do. Very important that at home you will do that. In accordance with what I told you, do you know MATLAB?
Yeah.
No problems. If you know MATLAB, no problem. The course is also for the students who don't know MATLAB. I try to introduce, but it's a shame very quickly because otherwise I cannot tell you about Kalman filter. But I
Uh,
will upload working files. This means once you are at home, you can repeat what everybody can repeat what I try to explain.
okay, thanks.
Yeah, no problems. Any questions, please. But believe me, if you come to the lecture, will be relatively easy to realize I hope to understand or to use in the future Kalman filter. Kalman filter is extremely important algorithm. Your name is Murabak. I pronounce it correctly?
You call me just Murat.
Murat. Did you hear about Kalman filter?
No, no, it's my first time.
First time, yeah. In general, identification. At this moment, we are speaking about identification. We will see another observer, not directly Kalman filter, because I need to introduce the Kalman filter with a different observer in the sense. Okay, other questions? Okay, if no question, we will see again just online again. I have the permission to do that. And next week, same time, same same time, same place. Excuse me, a little bit ill. Material is there. The video I will try to look how is the form because my voice is a little bit strange, but it's not a problem. Very important if you can use. I will send you or let me see when I am in Lunenburg if I can realize a repository in which you can look again at the ledge. Thank you to be here.
Herr Marcorelli,
Ja, please.
haben Sie vielleicht nach der Vorlesung, wenn alle gleich raus sind, noch einmal 5 Minuten Zeit oder ist es...
Of course, nein, ich habe Zeit. Jetzt,
Okay.
ich schließe
Recording. Mhm.
the record if I am able to do, and then we can stay here, of course. Where is there now? No, I don't see. Should be somewhere here. We cannot see because, as I told you, I, I I did the last time for the first time. Should be here something to. Now